What do you do after you drill the wellbore? Say we drill our wellbore, and let me make my wellbore a little bit bigger because I need a little bit more detail here. So what do we do, guys, after we drill the wellbore? Yeah, right. You may want to cement. Let's say this is an open hole wellbore. So you're going to cement it, put your casing, and what about after that? You cement it, right? We say, well, we cement the wellbore. What do we do after? Before you do a production, you may want to improve a little bit more your wellbore. So sometimes you have to clean up this region around here to, for example, get rid of the mud filtrate. And in order to do that, or to bypass the mud filter region, sometimes what you do are perforations. And let me do perforation this side. I'm going to do something else on the other side. And those perforations it's just rock failure at very high strain rate. And when you analyze those, you need equations a little bit more complicated than the ones that we're going to discuss, because the strain rate is so fast that your material is going to change. It's not going to be the same as at very low strains. We're talking about very high strain rates here and involving failure, right? So these perforation, usually you have explosives that will fail the rock in tenths of a second or less. So we could do perforations, or we could also, if you want to really bypass that region, you could do a hydraulic fracture. Hydraulic fractures have been done for over, I don't know, 60, 70 years more or less, and it is a very common practice. And now today they are done at a much bigger size and a much larger number than before, but they have been done for tens and several decades. So you could do that, and also a hydraulic fracture is another type of rock failure. It involves inelastic deformation. Before I continue with this example, I have another example about inelastic strains. And for that, we're going to go into unconventionals. So if you're working on an unconventional field and you go to the source rock and you drill a horizontal wellbore there, usually what you want to do in order to maximize your surface area is to put as many fractures as possible, right? Those fractures will, in order to maximize the surface area, should go perpendicular to the minimum principal stress. And let's say that you start a fracture over here, and we're going to assume that this is more or less a vertical plane. So this vertical plane is a fracture like this, and we're going to assume it's not growing into the next formation. If your objective is to get as much surface area as possible, you may be tempted to put your fractures as close as possible too, right? But there's going to be a problem with that. Of course, let's assume that these are all vertical fractures. At some point, you don't want to put them too close, because it's at least, if you were to put a fracture, you are a molecule of oil over there. If you put a fracture, say, over here, then it's going to take more or less the same time to get there than to get there. Or if we are assuming an open hole condition, also the same time as getting it there. So you don't want to put your fracture too close, because that's going to be unnecessarily too close, right? But there are some other reasons for not putting your fractures too close. And what is that? You guys are familiar with that? No? No. It's something which is called stress shadow or stress interference. Basically, say you put a fracture here and you prop that fracture. So now it's open. Because of that, now you have changed the stresses around the fracture. Now you have more horizontal stress than you did before. So if you were to put a fracture very close, like over here, in order to maximize surface area, this fracture may feel what is the state of stress from the other fracture and start to bend like that. And if you were planning to put all of these at the same distance from each other, this one now is even closer, and this one is propped as well. So this one is going to even maybe make this one to curve even more. And you may end up with cases in which you have a fracture that grows a little bit and that goes and hits the other. And you want to avoid that, of course, because what you thought that was going through the entire plane, actually it is not. If you were to do calculations with linear elasticity and just linear elasticity, you will tend to find that these stress shadows tend to be very large. But in practice, actually, they are not that large. In practice, you can put some of these fractures closer to each other. And that's because in these kind of formations, so let's say if we assume this is linear elastic, that is what you would expect from the rock and from a simulation if it really behaves as linear elastic. But if you were to do and analyze a elastoplastic model, you will tend to see that when you consider that additional plastic strains, these stress shadows do not get that far. Of course, you're going to get some stress shadow, but if you ignore the elastoplasticity, you may tend to put your fractures a lot further away than you would actually need. And this is because, again, the difference between elastoplasticity or inelastic strain and linear elasticity. Okay, so we know that inelasticity also plays a role over here. And after you complete and you're ready to start lowering the pore pressure in the formation and produce fluids, and this is when you get into the production phase. And into the production phase, you're going to have several types of inelastic strains. First, you can have, as we have seen before, compaction, or you can have compaction beyond the elastic limit. If you remember when we were analyzing depletion stress path, we had here J2 and here I1, or mean stress and deviatoric stress. And we said that if this is the shear failure, and we had here a compression yield. So either if you start somewhere over here and you go through this limit, or you go into that limit, you're going to experience inelastic strains. And if you experience inelastic strains, again, this formation is going to get thinner, and you can produce settlements on the surface. The geotech guys, can you tell me what's going to happen with the casing over here if you have this settlement? Down drag, right? How is that called in foundations? As far as I remember, it's called negative friction, right? Or something like that.
I mean, I've just heard it called down drag.
Down drag?
Yeah, we just called it down drag in foundations.
Okay, so if I remember well what Dr. Main taught me, he called it negative friction or down drag. Okay, that's a new term I learned. So sometimes you can put so much force because you know now all the rock and the semi is going down and is hanging by friction on the casing. What that can produce is casing failure. So your casing may buckle in compression. I heard of a very good example about this recently. I don't know if you guys are familiar with, I think I talked before about methane hydrates. So methane hydrates are an important hydrocarbon resource. And there are some countries like Japan, they are trying to Japan, Korea, India, are trying to get this gas from methane hydrates as soon as possible, trying to mature this technology. But sometimes they have this problem of production, a lot of compaction, and the casing experiencing compression here on the top, and in this region where, imagine if this section goes down, you can also expect tensile failure. So you can fail your casing if you have a lot of compaction. In addition to some problems that you may have in the surface because of settlement of the surface or subsidence, right? So compaction, subsidence, all of that. Notice that also if you compact this reservoir and this one gets next to the accompanies that formation, you're going to also be causing likely fault reactivation as you do that as well. And that fault reactivation, it's also another example of an inelastic strain. And one more thing, also related to production in all types of uncemented sediments, usually as you start producing, the fluids go into the wellbore, and the fluids, they have a viscosity, right? And if they have a viscosity and they put drag forces on uncemented media, they may cause those particles to move. As they move, they get into mix with water, with oil, and they flow up the production tubing. And as they do that, you could imagine that here you make these perforations larger and you have more and more compaction. That's a phenomenon called sand production. And sometimes in some places it can be very severe and it can be very bad. Actually, again, this case of methane hydrate production in Japan, they have problems because of significant sand production. All right, so we're getting almost to the end of the examples. Sometimes you cannot only do production, but you can also do injection, right? And if you do injection, also you can have fault reactivation. And if you were, for example, also to dispose some of the produced water in another formation, that would be another example of fault reactivation. Okay, so I'm going to get back later to wellbore stability, okay? Before we we finish the lecture today. But all of those are examples of inelasticity. Mostly shear failure in here, but some of those involve tensile failure, like in wellbore stability and in hydraulic fracturing. All right, so let's go through the theory that's going to help us analyze all of these processes. As we said before, we're going to check the limit on stress, and that's what we call a yield stress. And this is a perfect plastic material. And basically, when we do that, we can write that a function of the stress tensor and make that equal to a constant. So that's basically that, right? So here, the simple version of this is to say if sigma is equal to sigma y, that's failure. That will be in one dimension. In 3 dimensions, and to make it more general, we need to talk about the stress tensor. So a function of the stress tensor is going to be equal to a constant. We can relax a little bit this equation if we, or we can write it in another way, say, okay, I'm not going to look at the stress tensor, but I'm going to look at the principal stresses. And the direction also of those principal stresses. And that's going to be a function of a given constant k. So I know the principal stresses, I know the direction of those principal stresses, and I equal that to a constant. That is what it's called a failure criterion. It's just an equation. We can simplify this a little bit more, but it requires an assumption, which is a very important assumption. What about if I told you that we can write this same failure criterion, but just as a function of principal stresses? Would you believe me if I said that? What is the assumption involved in doing that? Isotropic material. Very well. If your material, like most rocks, is anisotropic, that, for example, the tensile strength in direction y is not going to be the same as the tensile strength in direction x. And because of that, you not only need to know what are the principal stresses, but you need to know how those principal stresses are oriented with respect to the anisotropy of the material itself. Otherwise, you cannot solve, you cannot apply that equation. But if you have an isotropic material that you assume, for example, in this case, a tensile strength is the same in all directions, and now we can write a shear or a tensile failure criterion or a failure criterion in general just in terms of the principal stresses, only by assuming there is isotropy, okay? If you're working with anisotropic materials, as most rocks are, this step is not going to be valid. You need to go one step further. Okay, so very similar to that, also you could write an equation for an isotropic material, which is a function of the indeterminates of that, and you could equal that to a constant. It's not going to be the same constant, right? All right, okay, so let's see how we write these equations. And we're going to start talking about very basics, solid materials, but we need to do this in order to get to the more complicated ones. Are you guys familiar with the Tresca Criterion? The Tresca Criterion says that if you plot here shear stress and effective normal stress, and for example, you're doing a tension test on a bar where this is sigma, and it's going to be, of course, it's going to be sigma n, because this is just a tension test. If you have no stress from the sides, one point is going to be there, and the maximum diameter of the Mohr circle is going to be given by a limit of this line, in which at failure that Mohr circle touches that line and gets to a value which is the yield stress. Right? Here we are increasing stress until you get to the yield stress. And therefore, if this is the yield stress, this is the minimum principal stress, this is the maximum principal stress, and this line is going to be at sigma y divided by 2. And what the Tresca criterion is going to say is that sigma 1 minus sigma 3 has to be equal or less than sigma y. As long as you fulfill that condition, you are in the elastic domain. You cannot go beyond that point. There is no possible solution for having a maximum principal stress minus the minimum principal stress larger than that number. This is a failure criterion which is mostly used for metals. Why? Because this is what is called a stress-insensitive failure criterion. And it is stress insensitive because it just looks at the difference between the maximum and principal stress, and it doesn't care about the mean stress. So this thing could be the same as having a Mohr circle over there and a Mohr circle over here, the same size over here. The only condition of this failure criterion is that diameter is not bigger than this amount, or the radius of the Mohr circle is not bigger than sigma y over 2. As long as you're there, then you're good. So that would be the analysis in one dimension. Okay? Let's try to see how this will work in 2 dimensions and then in 3 dimensions. Let me first write these equations in which these ones are the same as what I have before, but now I'm going to work with these principal stresses with Roman numbers that are not necessarily sorted by magnitude. Okay, here any of these could be the maximum principal stress, or any of those could be the minimum principal stress. It's just I'm just computing principal stresses, and I'm not sorting them. Okay, I just want to make this a little bit more general. So if we continue with this Tresca failure criterion and we expand that to 2 dimensions, let's see if we have the time to get 3 dimensions. Yes, we do. I could plot now here stress Roman 1 and a stress Roman 2. And what Tresca is telling me is just that the difference between those stresses is not going to be larger than the value of sigma y, right? And furthermore, in this case, I'm going to have sigma 3 equal to 0, okay? So if I apply the Tresca criterion, and let's say sigma 1 Roman is the maximum principal stress, and the other two are 0, so this is 0, and this one to be 0 will be a point over there. The maximum value I can go, in this case, is going to be sigma y, right? And even if I increase sigma 2 and sigma 3 remains to be 0, I can go up to a limit. Let's now assume that sigma 2 is the maximum principal stress. Sigma 2 is the maximum principal stress, and the other two are 0. That would be start over here, and I can increase it also up to sigma y. And if I increase now this Roman 1, but this one is still is 0, I can go and define a line like that. And this is also an isotropic material, so compression is equal to tension. This will be the compression side. This is going to be the tension side. And again, this is going to be minus sigma y, minus sigma y. I can do the same thing I did before. And what's going to happen when I have this one stays equal to 0, and I have, let's say I have negative sigma y over 2 here. What is the maximum stress I can have in sigma Roman 2? Plus 0.5 sigma y, right? And that, if I extend it, is going to be a line that goes through that. So now, by doing that, by putting all those equations together, these three equations, we define what is called a locus of shear, or in this case shear, but in general of yield. A yield locus or a yield failure line. But it's a collection of lines, you see? So what this is telling you, according to the Tresca criterion, is that you can be anywhere inside this, but not outside. As long as you're inside, it's fine. But you cannot be outside that region. This is the limit of all the possible state of stresses. And we're going to take this a little bit further now, and we're going to go into 3 dimensions. And we're going to define what is a failure surface. So let us now plot. This is a very difficult plot, guys. So if you can do it, that's going to be very good. In which we're going to put, let's say, sigma Roman 1, sigma Roman 2, sigma Roman 3 over there. And any state of stress, we're going to plot it with its principal stresses. Okay? Before we do that, we're going to define something. If I have an isotropic state of stress, so let's say that this is a given number and a given number which is the same, and this is also that same number but in that direction, the axis that connects the center with that point is going to be a line which is called the hydrostatic axis. In that axis, always all your principal stresses are the same. So that's the line also where if you have an isotropic state of stress, it will plot always in that line. So in the hydrostatic axis, sigma 1 is equal to sigma 2 is equal to sigma 3 isotropic state of stress. All right. So if you do not have an isotropic state of stress, then what you can do is you can plot that, and you will see that that's going to be always a combination of an isotropic. As you remember that we did before, we partitioned the state of stress into an isotropic tensor and a deviatoric tensor. Well, in this case, it's the same. Any state of stress in this space, you can partition it into an isotropic state of stress plus a given deviatoric stress. And in that space, we're going to see that the Tresca criterion is going to look like an hexagon like this. Well, I told you it was a difficult plot, so let me try again. I need to draw an hexagon in 3 dimensions and at an angle, so which is not very easy. And let me move this a little bit further. Now this is tricky, guys, you see? Not easy at all. Okay, I think I managed to get something more or less okay. The Tresca criterion is going to be this prismatic element which results as kind of an extrusion of an hexagon in 3 dimensions.
Is the cross-sectional area of that hexagonal prism going to vary with how far along the hydrostatic axis?
No, because the Tresca criterion is a stress insensitive criterion. So the sides, the length of the hexagon sides is going to be always the same. Either if you go infinitely in tension or infinitely in compression, it's going to be always the same. And this Tresca criterion is good for metals again, and for metals within a reasonable range of applications. Again, if you were to get some metals under a very, very high confining stress, very likely you will start to see some influence of friction as well.